Hi class, today we're talking about the rates of change in trigonometric functions. So really this is just a review of rate of change and we're applying them to sinusoidal curves. So let's remember that the average rate of change between 2 points, x1, y1 and x2, y2 is measured by the slope of the secant between those 2 points. So really you're just using the slope formula. M equals y2 minus y1 divided by x2, divided by x. Why is it doing that? Okay. Divided by x2 minus x1. Okay, just a grade 9 slope formula. So it's just the slope of the secant between those 2 points. The instantaneous rate of change, however, between A and a point F at A, at a given point A and the y value is F at A, is measured by the slope of the tangent at that point. So remember, we use the difference quotient. So the slope is equal to F at A plus H, where H is a very small value, minus F at A, all divided by H. Okay, and you make H very small. Okay, and you do that at least 2 times to see what your slope is approaching, and then you make an estimation about the instantaneous rate of change. Remember, this is really just the slope of the secant. It's just that the second point is very, 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 very close to the first point, so it's approaching the slope of the tangent. Okay, so if you have a sinusoidal curve, so here's a standard sinusoidal curve, up, down, and back up again. You'll notice that the slope of the tangent line is the least, so as low as it possibly can be, halfway between the max and the min. That's because it's at the steepest negative curve there. So on a typical sine curve, that would just be on the axis, but obviously if it's been transformed or translated, it could be anywhere else, or if it's on it, but it's halfway between the max and the min. So on the axis on the way down. Okay, the slope of the tangent is the greatest halfway between the min and the max. So here's the min, here's the max. So halfway between, your tangent will have the steepest possible slope. So this is the steepest negative slope. This is the steepest positive slope. Everywhere else, it will kind of go up or down. So see, after this, it'll become less and less steep until it becomes 0 at a maximum, and then less steep, and then more and more negative as it goes down again. All right, so therefore the absolute value of the slope is the greatest at any y values that lie on the axis. So any values that lie on the axis. This is a really important point. Okay. The following chart gives the measure of the distance of a child on a swing from the parent. So if we graph this, okay, we'll notice that our period is 1.6 because it goes from a distance of 3.8 meters away, closer to the parent, further away, and then a maximum distance again of 3.8. So if you go up by 0.5, 1, 2, 3, and then 4. Okay, and then we go up, you'll notice that a period is 1.6 seconds long. Okay, we're given up to 2.4. So we can go up by 0.4. So 0.4, 0.8, 1.6, 2.4. So this is time. And again, here I went up by, there's 1, 2, 3. And this is distance, okay? So we can plot our points. So 3.8 at 0.4, we're at 2.2. At 0.8, we're at 0.6. At 1.2, we are at 2.2 again. And then at 1.6, back up at 3.8. At 2.0, we're at 2.2. And here we are. So there we have this sinusoidal curve. Okay, so describe how the speed changes. So recall that speed is just the absolute value of slope, so the magnitude of slope. Okay, so therefore refer to the steepness of the curve. It doesn't actually matter whether it's negative or positive. So between 0 and 0.4 seconds, what's happening here? Well, the slope of the tangent is getting steeper and steeper. Yes, it's getting more and more negative. So that means since the slope's getting steeper, that the speed is increasing. Now from 0.4 to 0.8 seconds, the speed is decreasing. Okay, because then the slope of the tangent would get less and less and less as it approaches the minimum. So between 0.8 and 1.2, the speed is increasing again. Okay, and then between 1.2 and 1.6, the speed decreases again. Okay, so this is going to occur and reoccur for every period. So here to here we have speed increasing, here to here decreasing, increasing, and decreasing. Okay? So find the average speed over time swinging away from the parent and then toward the parent. Okay? So away from the parent, so if they're away from the parent, the distance from the parent, that would be when there's from 0.6 to 3.8. So that's between the time of 0.8 seconds to 1.6. So there's that. So then the slope is just the absolute value of the change in the y values. So that's 3.8 minus 0.6 meters away divided by 1.6 minus 0.8. So that speed then is 4. So when we're using the units then, we would put meters per second because it's meters on the top, the change in the meters divided by the change in the seconds. So as it's going away, the speed is 4 meters per second. Okay, now toward the parent, we could look between 0 and 0.8 seconds. So you do the same process here, and you will also get 4 meters per second when you do the absolute value, okay? So remember, if it asks for speed, speed is always positive. Velocity would be negative or positive. So the negative just means the direction, and the number means the speed. Okay, create an equation that represents this situation. Well, the axis is halfway between the max and the min. So that's going to be your C value, and you're going to take 0.6, which is your minimum, plus 3.8, which is your maximum, and divide it by 2, and that gives you 2.2. Okay, your amplitude is just 3.8 minus 2.2. So that gives you 1.6. Okay, your period, if you take a look, like I said, is 1.6 seconds. So therefore, your K value is going to be equal to 2 pi divided by 1.6, which if you put in your fraction button, you'll see it's 5 pi over 4. Okay, so to do that, you can just do 2 fraction 1.6, enter, and that won't work. So 1.6, sorry, I'm having a problem with my calculator. You have to figure out how to get 1.6 to an integer, and if you multiply it by 2.5, you get it as 4. So then you do 2 times 2.5 to get to 5, okay? So you need to get it into a fraction where the denominator is not a decimal. Another way of doing this is that you could multiply both by 10, because you know that multiplying the denominator by 10 will get you to 16. Well, then you would have 20 over 16, which you know simplifies to 5 over 4. So your K value, remember, it cannot have a decimal in the denominator. So then you can say let d at t represent distance in meters from the parent at t seconds. Okay, so your would be d at t equals, okay, it starts at a maximum, so we just use positive cos. So we put 1.6 cos bracket 5 pi over 4 t plus 2.2. And that's your function. Okay? So estimate the speed at 1 second. So as soon as you say at, you should think that's instantaneous rate of change. So you let your h be some small value, like 0.01. Okay? So, and our t is 1. So our slope then is the absolute value of d at 1.01 minus d at 1 divided by 0.01. Okay, and you get a slope of 4.53 meters per second. Okay, then you can do a second calculation. So you can do where our h value is equal to 0.001 and see what the second estimation is, okay? If you need a reminder, a refresher of how to do that, you can go back to your chapter 2 videos. But you'll see it's approaching about 4.5 meters per second, the speed. Okay, estimate the instantaneous rate of change to find the fastest speed. So we have to interpret that the fastest speed occurs on the axis. So we have to identify at what time do we hit the axis. So if you go back to your table of values, the axis is 2.2. So we can see that at 0.4, okay, we have, at the time of 0.4, the distance is on the axis. So this is actually asking what is the instantaneous rate of change at a time of 0.4 seconds, or any of the times when you're actually on the axis. So you do your m here. So I did d at 0.401 minus d at 0.4 divided by 0.001, and you'll see that you get 6.3 meters per second. So because this is on the axis, we can say, we can conclude that this is an estimation of the fastest speed that the child reaches during their entire swinging back and forth. So because it happens halfway between when they're at the furthest and the least distance, that is going to be their maximum speed, 6.3 meters per second. Okay, so really this is just a recap of what we've already done, with the additional thinking about how speed changes or rate of change changes between a max and a min, and how that repeats throughout the sinusoidal curve. And again, the fact that the fastest speed always happens on the axis. So thanks for watching, guys. I hope you learned lots.